Hey guys, Mr. Herbst coming at you live from my basement. I'll be doing your notes from down here today. Pay no attention to the puppy over there on the couch. He's just here to answer questions if you have any. So I know, haha. Okay, so let me go ahead and share my screen here. We are moving on to chapter 11. We are skipping chapter 10 for now. Okay, chapter 11 is about states of matter, and this is something that you guys have all, we've talked about, we've learned about before. We went into some depth when you guys were in 9th grade. So a lot of this should be somewhat review for you. Okay, 11.1 is about gases. I mean, they're, you know, when we're talking about states of matter, we're talking about solid, liquid, gas. We're talking about how they change phase, you know, boiling points and melting points and vaporization, things like that. So again, should be pretty well reviewed, but 11.1 is about gases. Okay, so obviously real basic, gas is matter that's compressible, and it does not have a definite shape or a definite volume. Its shape and volume will change based on its container. Okay, so if we look at the diagram here, we have all these molecules of air, if you will, and we'll refer to air quite a bit. Air is just, it's a mixture of all of the different stuff that is in our atmosphere around us, like, you know, mostly it's nitrogen, there's carbon dioxide, oxygen, obviously, you know, and then a whole bunch of other, what we call inert gases. Just means that you breathe them in, you breathe them out, no big deal. Your body doesn't know any different because it doesn't absorb them anyways. Okay, so when we say that gases will fill their container, it doesn't matter what the container is. The container could be the room that you're sitting in, or it could be an empty bottle of pop, or whatever it happens to be. But those molecules, and the thing to keep in mind, I shouldn't even say molecules because it could be ions or whatever. I'll call them particles. The particles, if you notice when you look at the diagram, they're spread apart. And when those molecules are spread apart like that, you can compress them, okay? Eventually, if we're talking about something like oxygen, you know, you can compress it enough, and with the right pressure, you can get it to turn into a solid. Like that's what they use for fuel in the space shuttle. Okay, differences between gases, liquids, and solids. Again, this is review. Liquids and gases are fluid. We'll get to that in a little bit, but that means that the particles can slip and slide past one another. Solids, they're locked in place and they can't move. So kinetic theory, or kinetic molecular theory, so if you remember, kinetic refers to energy or the motion of something. And so we're talking about the motion of molecules, or the theory about the motion of molecules, how they move and how they behave based on how they move. There's a principle called Brownian motion. And if you look at the picture here, that's a pollen grain, and it's just sitting on top of the water in a room that doesn't have any air blowing. There's no air current. It's not even in a room. It's in a container or a vessel, and they track the motion of the particle, or the pollen grain in this case. And the pollen grain doesn't move in straight lines. Its motion is completely random. So the idea then with Brownian motion is that those tiny chunks of matter have random motion based on how they are interacting with other molecules or particles. So like this pollen grain, it maybe has a whole bunch of water molecules that are bumping into it and pushing it in different directions, and that's why its motion is random. So this is kind of the same thing. Kinetic theory, again, is all these particles of matter, they're constantly moving, okay? And if something is kinetic, that means it's moving, or if we think about kinetic energy, that's the energy associated with things that are in motion, okay? So gas particles will move in a straight line because there's nothing to oppose their motion other than other air molecules in the container or the room or whatever you want to think about it. So they'll move in straight lines until they collide with either another molecule or another particle of air or gas, or with one of the walls of the container. And then they'll move into a different line. It's kind of like air hockey. One difference between air hockey, you know, when you hit the puck on an air hockey table, it bounces all around and it goes in all sorts of different directions. But every time there's a collision with the sides, it steals energy away from the puck. That's not true when we talk about ideal gases. They have collisions and they don't lose energy. So if we think about the kinetic energy, right, we remember that that's 1/2 of the mass times the velocity squared, okay? The velocity, remember, is how fast something is moving essentially. And then obviously the mass is like the larger the particle, the greater its kinetic energy is going to be just because it's large. Like, you know, a smart car traveling 60 miles an hour versus a semi traveling 60 miles an hour. Obviously the semi is going to have significantly more kinetic energy because it's significantly more massive. One thing that affects this is temperature. And the temperature is a measure of the kinetic energy of the objects or the particles that make up the object. So the faster those particles are moving, the more kinetic energy they have, usually the greater their temperature. So if we want to get things moving faster, we heat them up. So again, air hockey pucks, they lose energy when they collide with the sides of the air hockey table. But when we think about gas molecules, they don't lose their kinetic energy because they have what's called elastic collision, okay? Those particles will rebound and they will be having the same energy after the collision as they did before the collision. So in that case, we don't have any loss of energy because of those collisions, right? So the kinetic energy remains the same. Inelastic collision would be like an air hockey table, and eventually that puck will stop zinging around on the table, or other things. If you throw a ball at a wall and it hits the wall and just it lands on the ground, obviously that's inelastic. Now we talked about ideal gases a minute ago, but those ideal gases are particles that are in constant motion. They don't have any attraction for one another, like they're not attracted to each other or to the walls of the container. So when they have those collisions, they are elastic. They don't lose energy from that. And that's just one thing to note with ideal gases. So one thing that's really different about gases and really important about gases that's different than liquids and solids is that gases can be compressed. Okay, it's the only one that can be compressed. Now you can compress a solid and you can squash it and change its shape because metals are malleable and ductile. Gases aren't that way. So when we think about like, if we have a vessel here and we have a volume of air, and let's just pretend we're starting off with the middle one, right? There are a certain number of air particles in that vessel. Well, if you were to depress the plunger, that means to push it down. Now all of a sudden, since there's less space, so we look to the one over to the left here, there's less space, but there's the same amount of air molecules. Well, the inside pressure is based on how many collisions there are with those particles with the inside walls of that container. That is what increases the pressure. So when we depress the plunger, it increases the pressure, and vice versa. If we pull the plunger out, we increase the volume, so there's more space. When there's more space, there's less collisions with the inside walls, and so the pressure decreases. Okay, this is how air compressors work. So like if we were talking about an air compressor for like airing up the tires on your bicycle, or even a foot pump or a hand pump for your bike, you would press some sort of a lever would compress these gases. Those gases would then go through a tube into your tire, and we can compress those and we can create quite a bit of pressure doing that. Now, diffusion is a property of gases and liquids, or all, yes, gases and liquids. Sorry, I'm thinking fluids in my head. Those particles always go from areas of high concentration to areas of lower concentration. Like if you were, the example that we've used before is smelling something like in the corner of the room. The people that are closest to that corner of the room are the first people that are going to smell that. And as those air molecules dissipate or diffuse around the room, they become evenly spread throughout. If we were in class, I would take a drop of food coloring and put a drop in the water, and we would watch the food coloring start in one little spot where it'd be red or blue or whatever, and eventually it would spread to the rest of the water. Popcorn also is a great example. Like if you're downstairs or in a different room and someone's making popcorn, they're going to smell the popcorn before you because it's diffusing to them first. Eventually, it will diffuse to the rest of the area, whatever it happens to be, if it's at your house. And those molecules will be evenly spread throughout. And then eventually they'll get to the point where you're not inhaling enough molecules or particles of the smell particles, if you will. They're actually just molecules that have specific shapes that can be sensed by your nervous system. Eventually it'll get spread out to the point where you won't be able to smell anything, right? So the difference between like humans and dogs need very, very few molecules in order to be able to detect the scent of something. Humans need significantly more. Like, I don't even know, dogs' sense of smell is like hundreds of times better than humans. Diffusion is something that happens when there's a puncture in the container. If it's a sealed container under pressure and there's a puncture, like a puncture in a car tire, and it allows a little bit of those gases to be expelled out. That's what effusion is. I think that's supposed to be in red because I believe that's one of your, it is one of your keywords for the chapter. So gases will fill their container, and as they're filling their container, they're having collisions with the interior walls. Balloons are the same thing, hot air balloons, whatever it happens to be. That's what creates internal pressure. Now, pressure is just the force that is working on an object based on how many collisions there are with the surface. Now, we can create pressure just by pushing on something, right? So I have my hand and I can push on my hand, and that creates pressure. But that's a physical pressure, or I shouldn't say a physical. That's a pressure caused by the force of me pushing on it. When we talk about air pressure or atmospheric pressure, we're talking about the collisions of air molecules on the surfaces of a container, okay? So those molecules are constantly bombarding or crashing into both the inside or the interior walls of the balloon and the exterior walls of the balloon. Now, if the pressure on the outside of the balloon was the same as the pressure on the inside of the balloon, then the balloon would be all shriveled up, okay? Right now, there's significantly more pressure inside the balloon than there is atmospheric pressure pushing on the outside of the balloon. That's why it's able to inflate. That's the reason why hot air balloons work, because there's greater pressure on the inside of the balloon. There's more collisions with the inside walls of the balloon than there are on the outside walls of the balloon, so the balloon can rise up and, you know, go for a hot air balloon ride. So atmospheric pressure, and you probably remember because I stole this picture from the 8th grade Earth Science when we studied the Earth's atmosphere. But you recall that atmospheric pressure is created because of air molecules in a column of air pressing down or colliding with stuff, okay? Atmospheric pressure is what we call 1 atmosphere, or 101 kilopascals, actually 101.3 kilopascals. We'll get to that in just a little bit. One thing to note here real quick, if you notice in the diagram here, the infographic, there's significantly more air particles at lower elevation, so that pressure is higher at lower elevation than it is at, or I'm sorry, higher at lower elevation than it is at higher elevation. At higher elevation, the pressure is relatively low, and that's because of the lack of air molecules. So in order to measure pressure, there was a scientist long time ago named Torricelli. In fact, one of the ways that we measure air pressure or gas pressure is through what we call torr. Now, that's not the System International unit that we use. We use Pascal as that, but he was the first person that really started doing experiments. And so what he did was he created a little vessel here where the atmosphere would press down on this plate, and it would create interior pressure, and it would make the column of mercury in this, it looks like a thermometer. It's not a thermometer. It's what we would call a barometer or a manometer. And this would measure the amount of pressure in the atmosphere. If the pressure was 0, then the mercury would be all the way at the bottom here. You wouldn't probably even be able to see it. Now, 750 millimeters is what we call atmospheric pressure. So if the atmosphere is pressing down on, I suppose it doesn't help you guys if I point at it. If it's pushing down on this plate, which it is, it forces the mercury column to rise. And under normal atmospheric conditions, that measurement is 760 millimeters. So 760 millimeters is how far, or the distance, that the mercury can rise up there. Okay, so if we're measuring atmospheric pressure, we use what's called a barometer. And if we're using a different type of device to measure gases or gas pressures in a closed container, because obviously the atmosphere is not a closed container, but if it's a closed container, then we call it a manometer. So again, pascals is the SI unit for pressure. And in order to understand pressure, we need to remember that forces are measured in newtons, okay? That's capital N. So a pascal is equal to the force of 1 Newton, like pressing on something, per square meter. So 1 Newton of force on 1 square meter. So we get this handy dandy little thing. So a pascal is equal to 1 Newton per meter squared. Okay, that's what a pascal is. And for this chapter, it's not going to be hugely important that you remember all of these, but we'll be doing stuff with gas laws in the next chapter, and you're going to have to remember all these. It's going to be really important to have these on the top of your head. Okay, so 1 atmosphere is equal to 760 millimeters of mercury, right? That's how far the mercury will rise up and down the thermometer. Or it's also equal to 101.3 kilopascals, and that's what the pressure would be at sea level. That's how that's measured. So 1 atmosphere is the same thing as 760 millimeters of mercury. It's the same thing as 101.3 kilopascals. Because those can be, because those are equivalent, they can all be used as conversion factors. And we'll get into that at a different time in a different chapter. Okay, so Dalton's law of partial pressure tells us that total pressure of the mixture of gases is equal to the sum of the pressure of all the gases in the mixture. Okay, that sounds kind of ridiculous, right? Total pressure of a mixture of gases equal to the sum of the pressure of all the gases in the mixture. Basically what that's saying is if you have a container that has 2, 3, 4, 5 different types of gases in it, each one of those gases behaves a little bit differently because they aren't exactly the same. And so if we think about the pressure of, let's say, the example we're looking at here is helium, right? Helium and nitrogen. So the helium is going to behave a little bit differently than the nitrogen. So we take the pressure exerted by the helium plus the pressure exerted by the nitrogen gives us the pressure of the entire container of air. Okay, so doesn't matter. We probably won't be using this very much, but it's just one of those things to kind of keep in the back of your head that when we come up with the total pressure, it's the pressure exerted by the nitrogen atoms are different than the pressure exerted by the helium or the carbon dioxide molecules or whatever it happens to be. Okay, so that's it for 11.1. I'll pause for just a second and then we'll go with 11.2. Okay, so 11.2 is about forces of attraction. Now we know, like from working with magnets, and we learned a lot in ninth grade rather about this. There are different forces that attract atoms together, molecules together. There are things that push them apart. When we think about magnets, it's like the positive pole of one magnet versus the negative pole of another magnet. They become attracted, right? Because opposites attract, like charges repel. Would we have something that has 2 different poles, we call it a dipole, okay? And that term will come up here in a little bit, but I just wanted to clarify that really quick. I think it was mentioned in a previous chapter, but we didn't go into much detail about it. But that's what it is. It's just when an atom, or not an atom, an ion has, or a particle, let's say, has one side that's partially positive, one side that's partially negative, it creates a dipole. So the prefix di means 2, mono, di, tri, tetra, penta, hexa, hepta, octanona, deca. Remember, di means 2. So it has 2 poles, one positive, one negative. Okay, so the first one is what we call intermolecular forces, and those are the particles that sort of hold things together. Now, if we're thinking about ionic bonding, we have positive and negative charges. We know that opposites attract to one another, and that's what creates that attraction or the force that holds them together. If we're thinking about covalent bonding or molecules, then they are attracted to each other because they want to share a pair of electrons. Okay, that's what's creating their attraction for one another. And metallic materials are a little bit different because they have what's called the sea of electrons, and those electrons get passed back and forth very readily, and that's what that's what makes metals able to conduct electricity and things like that. Okay, so dispersion forces then are weak forces that result from changes in the density of the electrons in the electron cloud. Okay, so that sounds complicated too. Weak forces resulting from temporary changes in density of electrons in the electron cloud. Here's what happens. If you have atoms and they are coming into close proximity and they get compressed, it compresses the electron clouds and it squashes the that's probably not a great word to use, but whatever. It squashes the electrons closer to the nucleus of the atom, and it can create these dipoles where there's a positive part on one side and a negative part on another, and those two can become attracted. And when those dipoles come together, it creates a weak attraction for one another. Okay, and so it kind of holds them together. So then dipole forces are what we think about oftentimes when we think about like water molecules. That's an attraction between oppositely charged regions of polar molecules. Okay, again, that it sounds very scientific, but this is really easy to understand. Positive charges are attracted to negative charges. Okay, and we think about water molecules, they're positively charged on one side and negatively charged on the other side, so that makes them a polar molecule. So the positive side of one is attracted to the negative side of the other. And because they have those electrostatic interactions, okay, positives or like charges repel and opposites attract, okay, that's electrostatic interactions. They create an attraction for one another because the opposites attract, right? So this funny looking kind of S-looking thing just means partial, and that represents a dipole in a molecule or an ion or a particle or whatever it happens to be. Hydrogen bonds also create dipole-dipole attraction like we were talking about just before. This happens specifically when a hydrogen atom is attracted to some other highly electronegative atom. So we know from a previous chapter that oxygen is on the upper right-hand side of the periodic table. That actually looks left, but okay, so the upper right-hand part of the periodic table, and that's where we have atoms that have high electronegativity. Oxygen is one of those. So when we have oxygen being attracted to any of those on the upper right-hand side of the periodic table, it's going to create hydrogen bonds. This one is going to be between hydrogen and oxygen. So these are water molecules, right? The red part, the larger atom, is going to be the oxygen, and then the two blue ones are hydrogen. Okay, so the positively charged hydrogen part is going to be attracted to the negatively charged because we have two lone pairs of unpaired electrons on this side. So that creates a negatively charged side here and a positively charged hydrogen because the electrons are being shared in the middle, and that creates polarity and hydrogen bonding between those. Okay, so we'll get into that hydrogen bonding in a little bit here. We talk about surface tension and things like that. Let's see what's going on here. Oh, you got to be kidding me. Sorry, guys, I just got a notification that recording wasn't happening because I wasn't signed in, apparently. I don't know, it says it's recording still. I'm just gonna keep plugging away here. Hopefully this works out. Okay. So 11.3 is about liquids and solids now. Liquids are significantly more dense than gases, meaning that the molecules or the particles in the liquid are held together much more. And liquids cannot be compressed, or just in general, they can't be compressed. It takes a tremendous amount of pressure on gas, or on liquids rather, to compress that liquid, and it only will compress a little tiny amount. So we basically consider liquids to be incompressible. So again, liquids are fluid, and so are gases. Okay, the molecules are able to slip and slide around one another, and that's what gives something the property of being liquid. So there's kinetic models of liquids, and that basically says that liquids are going to fill the shape of whatever container they're in. And those liquid molecules, unlike gases, they don't move in straight lines, okay? Because they're having to slip and slide around and pass one another. They won't move in straight lines. One other thing that's important to note is that they tend to puddle together because there's an attraction towards the particles that make up the liquids. Like if we're talking about water, the water molecules have an attraction towards one another, so they tend to create pools rather than just laying out on surfaces in a thin layer. Viscosity is something that we've talked about before, actually several times. But we think about viscosity, and that's just the measure of the flow of a liquid, okay, or the resistance to flowing. Okay, so the more viscous, or the higher viscosity that something is, the thicker it is. So we think about the difference between like water versus honey, or syrup, or whatever we think about. Those syrups would be high viscosity, water would be very low viscosity. Okay, so surface tension we mentioned just a little bit ago. Surface tension is the measure of the inward forces that are pulling those particles together. Okay, so if we look, this is a picture of a water strider. We've seen this picture before, or something similar to this before. If we look at the particles on this side over here, those particles are pulling together, right? Because they have these forces holding each other together, you can exert downward force on that. And as long as that force isn't too great, then whatever it is, a water strider in this situation is going to be able to just remain on the surface. It won't sink down into the water. Now, I've done this before with a paper clip. It's kind of hard to do, but I have done it a couple of times with a paper clip. If you want to give it a try at home, it might help if you put some salt in the water and then see if you can get a paper clip to float on top. The salt molecules will intersperse or diffuse themselves. They're not molecules. Salt ions will diffuse amongst the water molecules, and it will create a higher density water, and you'll be more likely to get that paperclip to float. But if you're bored, give it a try. Okay, so surfactants are a thing that that lowers the surface tension of water. And what happens is when we reduce the surface tension, or the attraction for the water molecules to one another, it helps to break up dirt and oils and things like that. So soaps and detergents are what we call surfactants, and like dry cleaning and stuff like that. Basically what that is just a surfactant, and it creates a situation where the dirt is able to be pulled away or dissolved easily. Cohesion and adhesion are two properties of liquids that we've talked about before. Co means two, right? Adhesion is a different, or like the opposite of cohesion, okay? So cohesion is attraction of like molecules to one another. So water molecules want to stick together. This is really important when we think about really tall trees like sequoia trees and things like that. And they're hundreds and hundreds of feet tall. And in order for water to make its way all the way up to the tops of those trees and resist the force of gravity pulling them down, it has to have cohesion. Those water molecules have to want to stick together, okay? And as they do that, it pulls water or draws water up the tree. Adhesion is a little bit different. Adhesion happens when there's an attraction for molecules that are unalike or that are different, okay? So the molecules of the container here are different than the molecules of water, but the water molecules still have an attraction for the walls of the container. The same thing happens in the straw. We see this little area where it dips down right there. We've talked about that especially when we're measuring using graduated cylinders. You always measure from the bottom of the meniscus, because water or whatever it is being pulled up the sides of the container because of adhesion. Capillary action is a little bit different. That happens when there's a thin film that draws water up it, like straws have capillary action. We have capillary tubes that are these really thin little tubes, like you might see if you ever had a blood, like a finger prick for a blood test. There's capillary action that draws the blood into the little tube space. It's also the same thing that lets paper towels work. So there's very small spaces between the fibers that are making up the paper towel. And so water molecules get in between those fibers and they get drawn in because of that. And that's another thing. You could just take a paper towel or really any kind of paper and just put a little tiny bit of it in the water and you can watch it being drawn up. Okay, solids are a different type of material, obviously, than liquids and gases. And what makes them solid is the fact that the molecules or the particles that make them up are tightly packed together. They aren't able to slip and slide around one another. And because of that, they have a definite shape and they have a definite volume. Okay. Now, could we take a hammer and pound something? Well, sure we could. And that would change its shape, but now its shape is still definite. It still has a definite shape, and it's still going to have the same volume that it did before. I could take a bar of gold, pound it out into a huge flat sheet, and it would still displace the same amount of water as it would if it were in the block. So crystalline solids are a little bit different. They have particles that are arranged in a very specific geometric pattern, meaning that the angles are very specific between the atoms and things like that. When we think about like the crystal lattice, oftentimes we talked about this in 8th grade when we were learning about minerals. Minerals have crystal lattice structure. That just means that the atoms are arranged in an orderly manner. Okay. Now, obviously, we have something, whatever material this happens to be, the unit cell of that would be like 1 cube of it. So there's 3 different categories of crystalline solids. There's atomic solids, molecular solids, and then there's the covalent network solids. The atomic solids are only atomic solids that we have are noble gases. Okay, and that's because they don't have attraction for other things. So they don't have any of those intermolecular forces. Molecular solids then are molecules that are held together by some of those forces we talked about earlier: dispersion forces, dipole-dipole, and hydrogen bonds. Those are what we call molecular solids, and those attractions are relatively weak attractions, but still there's that force of attraction nonetheless. And then covalent network solids are atoms like carbon and silicon. Those are connected by covalent bonds. An allotrope, and we've talked about allotropes before. Allotropes are elements that exist in different forms, but at the same state. So they're both solids, but they're in a different form. So like carbon atoms can create graphite, like for a pencil, or they can create diamonds, or carbon is one of those that has lots of different allotropes. They can create graphene and all sorts of different compounds that come from carbon. It just has to do with how the carbon atoms are arranged in those particles. Okay, 11.4 is about phase change, and I'll just pause for a second, and then we'll keep plugging away here. Okay, 11.4 is about phase change, going from solids to liquids to gases, and then ultimately plasma. Plasma doesn't really occur very naturally on Earth, except for a couple different conditions. Okay, the melting point is pretty straightforward, right? That's the temperature at which the crystal lattice breaks down. Okay, now we think of the melting point, it's like, oh, something goes from a solid to a liquid. Boom, that's the melting point. It's a little more complicated than that, but generally, yeah, you're right. Something goes from a solid to a liquid. But the reason it's going from a solid to a liquid is because the thermal energy that gets transferred into the material becomes great enough that it makes those particles start to slip and slide and move around one another, and then they become a liquid. Okay, so again, increasing temperature, things become liquid. Now this one you can see on the right side, those particles are just starting to become liquid, and on the left-hand side here, there's still crystal lattice structure. The crystal lattice hasn't begun to break down yet. So vaporization then is when a liquid then becomes a gas. Sometimes we call that a vapor. Okay, so vaporization is when a liquid becomes a gas. So as we increase the kinetic energy, okay, so we get particles moving faster and faster and faster, eventually, excuse me, eventually we get to the point where those molecules or particles, whatever they happen to be, have more energy or are moving faster than they are on the surface of that material, whatever it happens to be, and then they can escape. All right. So, you know, if we look at this as kinetic energy is increasing, and the increasing maybe because we're shooting ultraviolet radiation at it, or maybe we're, you know, have it under heat, we're heating something up, it gets hotter and hotter and hotter, right? When we get to this point where we have all these molecules, and the molecules start to disappear, they don't disappear, but escape from the liquid and end up turning into a vapor or a gas. Okay, here we can see vapors and gases. So this is vaporization happening right here. Evaporation happens when liquids at the surface are evaporating, okay, or they're escaping, and that's called evaporation. If there's something, if it's happening throughout the material, okay, like when you boil water, the bubbles form for the most part down on the bottom because that's where the heat is. That's where most of the thermal energy is being absorbed. And when the thermal energy gets absorbed, those molecules start moving faster. Eventually they vaporize, and then it creates these bubbles, and boom, they come up to the surface. And then we also have all the steam coming off as well. Okay. So that's the difference between vaporization and evaporation. Okay. Evaporation happens just on the surface. Vaporization happens throughout. So vapor pressure then is the pressure that gets exerted onto the liquid by the atmosphere around it. Okay, so when we think about vapor pressure, we're thinking about the pressure in the atmosphere around the liquid. Okay, so there's particles of air that are colliding with the surface of the water in here. Now, because of the thin neck on this flask, there's not a lot of air that's able to get in there, so it helps to reduce the amount of vapor or evaporation that's happening. But there is collisions with the air molecules on the water that's in that container, in that flask, and that creates vapor pressure. The boiling point is pretty straightforward. That's the temperature at which, this is going to sound complicated, the temperature where the vapor pressure of a liquid is the same as the atmospheric pressure. So what that means essentially is that the pressure in the liquid is the same as the pressure being exerted on it from the atmosphere. Okay, so there's pressure on, well, let's just say I have a glass of water here. There's vapor pressure pushing down on it. And on a day where the vapor pressure or the air pressure is relatively low, we have a lot more evaporation that can happen because there might be higher or greater pressure on the surface than there would be in the atmosphere around. Okay, so that's the boiling point. It's a temperature. So if we're talking about water, it's 100 degrees Celsius or 212 degrees Fahrenheit. Sublimation we've talked about before. That's when a solid turns to a gas without forming a liquid first. One of the things that we see happening, especially during the winter time, you know, the temperature, you know, in January, February around here, it may go days and days where the temperature doesn't go up above 0 degrees Fahrenheit. But there is a buildup of ice on the road because we drive over the snow and it compresses and eventually forms ice. But eventually that ice will sublime away. And if the air temperature is cold enough and the pressure is low enough, it can start to do that. Compressed carbon dioxide, or dry ice, if you will, it does that. So when we take dry ice and we put it in a container and it starts to smoke, that's not actually smoke, it's just turning into a vapor form, or the CO2 is turning into a vapor form. Okay, We have the freezing point. That's the temperature at which the liquid is going to change into a crystalline solid, right? Something goes from a solid or from a liquid to a solid. That's the freezing point. And then condensation is something else that happens. That process happens when we have the vapors that condense or come in contact with one another, and they will form little droplets. If it happens in the atmosphere, then precipitation or rain starts. It might happen on your pop can. If you have a can of pop that's cold, you just took it out of the fridge and you go outside on a hot, humid day, the air right next to the can can't hold as much water vapor, so they start to condense, and we end up with little droplets all over the surface of a pop can. Deposition is one that you guys are all familiar with, I'm sure. This happens when a gas or a vapor turns directly to a solid. That's like why you have to scrape your windows during the wintertime, because the molecules of water in the air are able to condense on the windshield of your car because it's a little bit colder, and it creates all this frost. So a phase diagram then shows us it's specific for a specific substance. Here we're talking about water, you can see. And it tells us at both pressure and temperature whether the water is going to be a solid, a liquid, or a gas, okay? So if the temperature increases, we know that eventually it's going to turn into a gas, right? So here's the boiling point, or the normal boiling point at sea level, and from here on out, that water is going to be turning into a vapor, okay? Now, going the other direction, it turns into a solid. We can see then that there's what we call the triple point. That's the point right here on the phase diagram. We're talking about water, where potentially water could exist in all three phases. Now, one thing to note is that we're measuring in atmospheres of pressure. In order to reach the triple point for water, the temperature, or the pressure rather, needs to be really, really low. Like here's 1 atmosphere of pressure. That's the pressure of the atmosphere pressing down on us. It has to be really low pressure and almost freezing temperatures in order to reach the triple point. So phase diagrams are really important for a lot of for science, because you can get a lot of information about different substances and how those substances will behave. You know, for example, we're looking at carbon over here. Carbon can exist as graphite. You've probably heard, oh, we can make a diamond. It just, you know, takes a lot of pressure and heat. Well, that's true. It does take a lot of heat. So we're talking, here's 2,000 degrees Celsius right here. And then diamonds can form, so we're almost at 3,500 degrees Celsius with extreme pressure. So this is 10 to the 4th atmospheres of pressure. This is very high pressure. Okay, so that's it for the chapter. I hope this stuff recorded. We're going to find out in a little bit. If you have any questions, please reach out, and I'd be happy to answer those questions for you. Otherwise, stay healthy, and I hope to see you guys in the classroom soon.